Good afternoon. Let's try it again. Good afternoon. Welcome. So this is the Intelligent Edge session. Got an interesting topic teed up today. So before I dive deep into what this session is about, what I would like to do is start with a brief context. The context is about a customer trend that we are seeing. We're seeing a convergence of a set of foundational technologies. And what we mean by that is customers are combining, Internet of Things, machine learning, and collecting data from physical devices, then using all that intelligence to sort of transform the business, reinvent customer experiences, and in some cases create, outcome-based economies. Whether it is GE trying to reduce wastage with its industrial 3D printing, NL creating a smart meter management platform, whether it is Thermo Fisher Scientific trying to monitor the lab equipment, analog devices monitoring manufacturing processes, Deutsche Bahn monitoring trains. Then you've got Vizio, which is like monitoring about 1 million televisions that have Alexa integration in them. Then you've got MLB StatCast, sort of ingesting about 15 petabytes of data, and then just trying to improve, fan base experience. Across all of these use cases, across customers of different sizes, different enterprises, what we are really seeing and hoping to do in this session is to distill it down and cover 3 things, right? First thing is, what is the intelligent edge, and why is it important? And want to sort of talk about the role of the cloud within that intelligent edge. The second topic we want to talk about is, we've got a customer solution showcase, wherein Sentient Science partnered with Tensor IoT and AWS to build a solution that really transforms the wind energy business. And I'm very excited to have Amin Shigani here, who's the CTO of Sentient Science, sort of share this session, and he'll talk about that topic. The last thing that I would like to do is talk about the AWS IoT partner ecosystem. And we're making a big push towards solutions and sort of have an announcement to make. Yeah? So with this in context, at Amazon, we're very customer obsessed. And what we mean by that is, we work backwards from customer pain points. And roughly, 90 to 95% of our roadmap gets built this way. So in every IoT conversation, we start with this question. What if you knew the state of everything, and you could reason on top of that data, what problems would you solve? So there are 2 necessary conditions in here, right? One is knowing the state of everything, and then reasoning on top of that data. So let's take a large problem like food shortage. We are adding about 83 million people to the human population every year. And the agriculture industry is just challenged to keep up with that population growth. Right? If you look at agriculture yield today and the population growth, there's a significant shortfall of just food supply. And there's a shift in terms of the industry towards more precision farming to sort of address this challenge. And the agriculture yield has to grow by another 1/3 just to keep up with this growth. So here's Yanmar. It's a $4 billion industrial equipment manufacturing company. And what they do is actively manage plant growth in greenhouses. And they're actively managing it to sort of optimize the right amount of water supply, the hydroponics, the environment conditions in terms of fans and air conditioners. And what they decided to do is deploy image recognition in these greenhouses. So they put in 12 cameras in these greenhouses that would collect data of images of plants, and based on that image recognition, optimize the conditions just to improve plant yield in those greenhouses. Now, as Yanmar, a lot of these greenhouses are not in the best connected environments. The best connection that you might find is a 3G connection. Now, do you want to sort of transport all of this image data that you collect back into the cloud for further processing? Or you want to be smart about it and just transmit only what is necessary in a smart format so that data that you send back to the cloud is still valuable with other data in the greenhouses, right? And in addition, you want to sort of do this back in the greenhouse so that you're able to optimize based on the imagery data that you collect. So at AWS, what we're really focused on is how do we make it easy for you to know the state of everything, and then being able to reason on top of that data so that you can really solve some of these business problems. So with this in context, what I would like to do is just talk about what is the intelligent edge. So what is the intelligent edge is about being able to process data closer to where it's being created without having to go do this back and forth to the cloud. Think about a car today. It's got about 200 sensors. It's generating about a petabyte of data a month. And you contrast this to the MLB example I gave you, and you've got 17 petabytes of data just for that one season, right? So as a business and as a developer and as an enterprise, you'll have to make this decision whether you want to process this data at the edgiest edge or back in the cloud. And so where you do it will depend on your use case, your solution requirement, your cost considerations. There might be other data sovereignty considerations that you may have to take into place. And what we see is there are actually 3 trends, and we like to call them laws, because these laws are going to stick irrespective of the technology sort of evolving. And then the first law is just laws of physics. Light can only travel so fast to the nearest data center. So if you want to make a decision that requires you to do it faster than the speed of light, then guess what? You'll have to make the decision yourself, right? The second thing is just laws of economics. Data has weight. It's going to cost you money to transport this data. And this third thing is just laws of the land. There could be other data sovereignty considerations that you have to take in place. Now, what's interesting about these laws is that they work in both directions. While for latency requirements, you want to process this at the edge, this data is going to be valuable sitting with other data in the cloud. The second thing is, while it's economics that might play a big factor in terms of network costs, the cheapest storage and compute is going to be found in the cloud. So in the end, I think what we're trying to do at AWS is to provide you with a set of tools and solutions and services so that you can make these trade-offs depending on your solution, your business need, your economics, and cost considerations. Now, this is an IoT topic, and I have to have some bold, big numbers in here. But if you look at Gartner's assessment of it, the first number is quite obvious, that there's going to be 25 billion endpoint devices across a variety of markets in industrial, in consumer, and commercial. But what is interesting, and probably what's not that obvious, is the number in the middle, which is that 75% of the data is going to get created and processed outside of data center environments and cloud environments. Now, if you look at the kind of devices that will create this data, they're all compute constrained and storage constrained. And this is where the cloud is going to be disproportionately important, because we are seeing a lot of IoT applications get built on AWS. Like I talked to you about the MLB StatCast app that was built on AWS. John Deere deployed sensors on 200,000 tractors to essentially optimize how they plant seeds depending on soil conditions. Now, the other aspect of this is there's going to be a lot of data that's going to get created. And this is Philips. They built their digital healthcare platform on AWS, and they brought in 390 million medical record images. That's roughly about 15 petabytes of data, and they're adding another petabyte of data every month. So this is where the scalability, the elasticity of the cloud comes into play. Now, in reInvent 2017, we introduced a new service called AWS Greengrass. What AWS Greengrass essentially does, it brings in AWS capabilities onto your devices so that you can drive local inferences and local triggers. Put in simple terms, it lets you bring in capabilities to whatever location you choose. And what this is allowing you to do is allows you to really operate devices even in disconnected environments. And you could choose to run them just like you would run as though it were connected to the cloud. It would simplify the programming language with Lambda capabilities, so you don't have to really worry about the embedded programming archaic interfaces that some of these devices require. And then the last thing is it brings in AWS-grade security to this platform. So with this in context, what I would like to do now is invite upon Amin to talk about the solution that they've developed in the wind energy business. Amin? Oh, thank you. I've got a clicker here.
Thank you. Thank you, John. Am I on? Hot. I think I'm going to need that. Thank you, Prashant. I am so excited to share the stage with AWS folks to talk about the partnerships that we've had over the year. But before I do, I'd like to recognize Ravi Raghunathan and Tensor IoT team for the great collaboration with my team to make this happen. So he's not with us today, I believe, but I'd like to make sure that he's recognized. My name is Amin Shigani. I'm CTO of Sentient Science. I lead the platform team, the cloud platform team at Sentient Science. My team consists of 3 groups, a material science group, a data science group, and a software and user experience group. I joined Sentient over a year ago, year and several months. And before that, I was part of GE Digital. I spent over 5 years building IoT solutions for the different GE verticals. I spent the formative years of my program in building solutions for emergency response management. I think the edge there was the person. The last system I worked on is the emergency alert system that basically delivers the amber and the weather alerts that we all get in our smartphones. We went live in 2012 before I joined GE. But today what I want to talk about is some of the work that my team, AWS and Tensor IoT, worked on over the past several months, specifically what we call a cold start use case. I'll get to dig deeper into the cold start use case, but I think the technology capabilities that we got a lot of help using Tensor IoT in the relationship with AWS is around the AWS IoT, which is a capability we didn't have before, and the machine learning capabilities, which is critical data science capability that they've helped us build in a short period of time. So before I get to dig into the use case, let me introduce a little bit the company I work for, our customer base, and what we do to give you a context of why cold start case was very critical for us to work on. So Sentient Science was founded in 2001 as an R&D company. It competed for SBIRs, it's short for Small Business Innovation Research. So for the first 12, 13 years, it secured over 30 million of competitive funding from the US government and different government agencies to build what we call a digital clone technology based on material science and computational science expertise. Beginning of 2013, after building and validating that digital clone technology in the aerospace industry, we began to move into the wind industry commercially, 2013. And the last 2 to 3 years, we've been successful enough to have over 220,000 assets, wind turbines under management, with a pipeline of 40,000 assets just within the current customer base. We serve the wind industry. It is 80% of our revenue. We continue to support the aerospace industry, especially in the government program. And we've had a couple of early engagements with railroad, or class 1 railroads already. We are just a little bit under 100 employees altogether. Most of the organization is in my team. We have had a good sustainable growth that resulted in an additional $30 million between Series A and B in 2016 and 2017. So this is the company. From a market perspective, Sentient is rooted in hard sciences, material science, computational science. We have a lot of accolades from NASA, Tibbetts Award at the White House, and some others in the material science capabilities. Our customer base, we have some of the largest wind operators in the world that are already on our platform. We differentiate between what we call phase one customers. We have several engagements with wind operators and suppliers, call them phase ones. The customers that we call phase two and up customers are ones where we have long-term master service agreements for their entire fleet over multiple years. And that's basically in line with our SaaS model. So we consider those to be more than customers, but rather partners. We have a large, I think, important base in terms of operator. A large deal with an O&M, a wind O&M is hopefully coming up and in the works, coming up very soon. I think a lot of us, I face this every time I talk to customers, and that's what I like to show this slide as to what we bring to the market, as opposed to many companies that do what we call prognostics based on this data science. The value proposition that we bring to the market, we have two complementary capabilities that we bring that we believe are very differentiating. One is the ability to assess and predict life based on the material characterization and properties of the different components within your asset. And the second capability that's related to that is the ability to then recommend what we call asset actions or insight that are also based on the material properties of the asset componentry. So when you look at the graph here, we have a color scheme by which we try to explain this differentiation. What we call condition-based systems, well-instrumented assets with sensors, they allow you to operate in the red and the gray all the way towards the left. So if a pattern is going to develop, I think a data science approach a machine learning approach will pick it up. If a particular crack shows up, a good sensor should pick it up. For us, that is too late to do anything significant to lower the cost of operating the asset. Material science capabilities and modeling enable you to have visibility into the asset at the level of a failure or crack, nucleation, and initiation phases. An ability to model at that level gives you now a longer period of time in understanding of the health of that asset. And with that longer period of time and that understanding of that asset, there is a lot more that you can do. And that's what we call, you can do life extension actions to make sure that since your asset gets into operations, going into a known failure, you can do something at year 4, 5, 6, 7 that could push that way longer. And if you can get a wind turbine to work 2, 3, 4, 5, 6 years longer by the way you operated in the former years, then you're able to get more energy for the same investment you make on the asset. So I think that's the value proposition. There is a lot you can do with condition-based monitoring. There's a lot that you can do using your data science and sensors. There is a lot more that you can do if you have that understanding across the life of the asset. So to be able to model at that level, we have a set of two things: modeling capabilities and tools and a process by which we do this modeling. So the digital clone nomenclature that I mentioned is the first thing you want to do to begin to have a digital representation of an asset is to create its digital clone or digital twin, pick your, or a digital representation. And I believe that what we bring in the market is that building that kernel model that represents the asset starts at the material level. So whether at the wind, so the first modeling capability is the ability to model wind loads. from an operations perspective. Second capability is your ability to model the drivetrain, the most important component, for instance, in a wind turbine. You can model the blade, you can model the generator as well. The drivetrain is the most expensive one and most complex in a wind turbine. And then we get to the subcomponents. Now, a drivetrain is an assembly. It has hundreds of components. Mostly they are bearings and gears. And your ability to go to the subcomponent level and understand how the bearing or a gear fails, fatigues, cracks, has nucleation that's showing up on the surface, the ability to do that is very critical to begin to create what we call the digital clone of this asset. So in this capability, like I said, we have tools, both tools to model, tools to do analysis, tools to do life prediction, and most importantly, because we don't build these assets, what we do is we use our lab where we reverse engineer the properties of this asset. So unlike a manufacturer, we don't manufacture this asset. So as we get to learn about a new gearbox model, which we don't have a model for, we get the geometry of that gearbox. So we would go to a shop and take geometry measurements. We get samples of gears and bearings. We bring them to the lab. We cut them up. We do material characterization. And we begin to reverse engineer how that particular component has been manufactured and how it will behave under certain loads. And basically, we build the understanding of the asset from the bottom up. So now that we have this digital clone that is rooted in the material science properties, we can overlay what everybody has, the operational data, the SCADA data, the fault alarms, the event data, and then we begin to use that model to understand how this particular asset in your particular environment is going to operate. So this is what we get to do. In my team, we're focused basically on taking this capabilities that we built over many, many years. The differentiation here is how do you bring it into the cloud and how do you bring it in a way that is integrated to drive a business value. So I'll start from the bottom up. We have been born from day one in the cloud, and I think we made a choice to go with AWS. So all the infrastructure that we have, we don't have anything in-house, is in AWS. And from a design philosophy perspective, if it exists as a service within AWS, we configure it and we move on and begin to build differentiation. The differentiation basically is in the middle layer. It shouldn't be modules, it should be runtimes, which is I have one color for everything else and 3 different colors for what we call differentiation. The red and the blue, the digital clone modeling, which I just described, the computational life prediction. These are capabilities that I would admit if you go to a supplier, a manufacturer, they probably have that because they have to design these components, they have to manufacture these assets, so they do have some of this understanding. That is something that's usually is vaulted. You couldn't get access to it even if you worked at these supplier companies. The second thing is the orange, which is the analytics and the machine learning. And these are basically the capabilities that allow you then to take the SCADA data, the time series data, take in the fault and alarms and other metadata and do some machine learning and AI. And I think bringing all together in a cloud platform is something that we feel very strongly is differentiated and it doesn't exist in the market. So I think to do that, like I said, you need a lot of help with the infrastructure to make sure that you have the speed and the scale that you have, but also you have the focus, that we focus, the small team we have on the differentiation of the infrastructure and the platform. So what I want you to remember is what we call runtimes, which is a technology stack where you can run the different models I've talked we have to build, from machine learning to doing life analysis to modeling basically the the system or the component within the asset. So this is where this concept of the cold start got born out. We are a small company. We're continuously, as a startup, trying to have an aggressive growth. And there are three impediments to our growth, and I think to many who work to provide a solution in the industrial side. Industrial companies, in the wind in particular, it is very normal to have a 9 to 1 year sales cycle. These are large enterprises. When you go outside of the US, some of them are semi-government entities. So that is something that for a medium-sized startup is very detrimental to the growth we want. So that's number one issue. Number two, when you talk to these companies, and because IoT, ML, AI, prognostics, I can get some data set and I can give you AI, I can give you insights and dashboards. When you get to talk to these customers, it's very difficult for us to explain what we are doing that's different than what you see. And it's outside of something that is tangible. It's hard to do. But we can't do that unless we get access to some data. So I think you have a cold start problem in AI. This is the same thing. So it's a code name for what we talked about. That's the second challenge. It's very hard to explain the technology based on slide decks, et cetera. So we wanted something that is different. Number three, for the customer we've worked with, and we do have 40,000 assets in the pipeline, 20,000 assets in our platform, there is a problem with the data we get from customers. And in my assessment, and I've worked with many, whether when I was at GE or now, and I can rate it between okay data to garbage data, which is skewed towards garbage. So it takes so much time to get to prepare the data before you can do anything useful to it. And I think something that can address that is going to help us again. That's the third impediment that we had to. So the goal there is that how do we then enable ourselves to engage with customers at 10x scale. So we are able to touch 10 times the number of customers we can touch in terms of our sales cycle. And how do we basically cut the sales cycle in half within a quarter? So I think that was the challenge. That's the business that we wanted to do. And we brought in AWS, we brought in Tensor IoT, and we said, this is what we wanted to do. We have some ideas. It's going to require technology. It's going to require scale experience, infrastructure, and of course, it's going to require some modeling behind it. So we've done the work. I've worked with AWS, like I said, since I joined, so a year and change. But this work started in the summer. So within the span of 3 months is what we have been able to use across different teams to build the solutions I'm about to discuss. So I think here, I think there's a creative way of, for the cold start initiative to start and have some tangible efforts, there are 2 places where we needed to, I think, focus on from an infrastructure perspective. As I said, we do have an ingestion, I would call it a version 1 data ingestion pipeline that we use. But I have nothing that is even closer to the customer edge. So we needed something that is more IoT-like one. And on the infrastructure, we do a lot of set of modelings. We have ways of running those models. I didn't have anything that resembles a pure, pipeline automated, cloud-based kind of runtime for all my models. And I think that was the second infrastructure that we needed to build. So working with folks in Tensor IoT with their expertise in AWS, working directly with AWS, at least SAs, we've been able to quickly put a solution architecture together and then get to work. So there are 2 pieces of this architecture. One on the left, on this side here, look at my hand, which is basically the IoT side. Currently, the work that I do with my customers, we have a philosophy that says, I meet the customer in whatever stage of their digital transformation. I'm not coming to customers to say that I'm going to help you with all your data problem. I'm saying I'm going to help you with running your asset more efficiently and lowering the cost of energy. So, and that's why we accept data from between the two spectrum I've talked about. But I needed something so we can have a lot more intelligent conversation where I can go to the customer I have today, the customers that I may have, that I do have some capabilities in terms of how you pre-process, quality, check your data before you send it to me, because we've built that. We do all that in the cloud. So on the left-hand side is where that capability is. And then as we move towards the right, we wanted to make sure that the models that we currently have, they need to be in a single place, run as a modeling suite for what we do. But also, we needed to build what we call a cold start model. And there are different set of data sets that we needed for it. So I think I would like to move from here to beginning to demo some of the pieces. And I'll reference this slide and what I'm showing to give you a context of what we built. So remember, we've spent about 12 weeks, several individuals from my team, Tensor IoT. We had a lot of help from, like I said, SAs at AWS. Of course, the infrastructure is AWS. And let me begin to show what we've put together. I think I'll show some UI that can give, all right. Okay, so this is my computer. So remember here, I'll start with the cold start concept here. And let me go here. Just make sure that I'm logged. There's internet and I'm logged in. So if you remember, what I said was I wanted something that is not a slide deck, that begins to speak about what I've talked about. What do we do, right? We do prognostics and predictions based on, and we wanted to do it without knowing that we are not going to have access to the data soon enough. The sales cycle is long, and the work with the IT departments and these industrial customers is as long. So what can I come in day one to the customer with that could begin to tell our story, our capabilities, so we can move forward? So what we said is, without any information from the customer, we're going to use a proprietary historical failure data of different gearbox model, different wind turbines that we have. And we probably have a coverage of over 30% of what's deployed in the market. So we will use that as a data point. And we will begin to use some transform learning capabilities for. The second is, when we go to the US, and this is not the entire US, there are some publicly available wind turbine information that is there. And we have access to some private, you have to pay to get that data, and there is public data. So this turbine belongs to this customer in this special location. It's been operating since 2008, for example. There is that metadata. So we collected all that. We cross-referenced it with what we have. We cross-referenced the public, the private, to make sure that we have somewhat good confidence. I wouldn't say high. Good confidence in the data we've collected. So that's publicly available data. We also looked at another data set, which is spatial data, so where they exist. USGS, for instance, has that. We also looked at climate within those along the lat for. So we looked at forests, we looked at the terrain, roads, etc. So we've collected all these publicly available data sets, and I'm not sharing a lot. This is really brand new capability we're trying to hopefully surprise the market with. We've collected 6 sources of publicly available data, our internal database, and we said, what type of modeling can we do to do some form of prediction, some form of prognostics about what could happen. So what you see here is that we have modeled about 60,000 turbines that exist in the US, and we're in the process of replicating this in Europe. It's difficult to do in China, but I think that's, the idea is that we're just going to do it for every single turbine in the world, about 300,000 of them. Because we have the process, we have the pipeline, we have the data set, we know how to do it. We just need to get some access to the public data, and we'll do. For the US, it's done. We have 56,000 turbines, different. What I'm showing here is that a subset of it and I'm showing this here because this is not news. If you ask me about my product, we already have this, and we can validate this data. So these are some of the customers we actually have. So when we do the validation, we train the data on what we have. We run it against things that we see how good we are. And I think we have pretty good models. I think version 1 of the model. So here you look, for instance, at, here it shows a large portion of wind turbines across the US. Some metadata about, this is the wind farm. When was it started? What type of capacity it has in megawatts. So just to give you, you have now a 2.0 megawatt. You have 3.0. I mean, offshores are bigger. So this is how you would get how many wind turbines are you. It's safe to divide this by 2 to know how many in that particular. And what we have done is we have used the data. We created a model that we've ran across the board. And what we have here is we can go to a customer, say Nextera. Nextera is a long-term customer for us. This wouldn't work. But we can go that in Ashtabula 2, this is where they are. So we're able now to locate where those, and remember, I have not talked to Nextera yet. And all of a sudden, I'm showing them this. I know which assets you have. I know how they're, more or less. I think we have some confidence as the geolocations because, and then I'm able to say that just based on the type of gearboxes you have and the modeling we've done, you have 3% failure rate across that fleet. And then because of the different whether it's climate, location within the wind farm, we can even begin to say, and this is, again, this is what will drive some really heated conversation that this particular one here, this particular one here, this particular one. It's mere classification. Now, I may be wrong, right? I can guess 10, and then they go back historically and they find out it's 5 out of 10. Now we're beginning to have a conversation. Well, tell me more, because what I'm saying is I have no data. I have absolutely no data that you've given me operationally to do a proper prediction, but I can do a good modeling of what you have. And then we can begin the conversation about underneath it. I have physics-based models. I have material models of some gearboxes. So I can say, for all your Clipper fleet, GE fleet, Vestas fleet, I already have models, but I don't have this and that. And if you give me the geometries, if you give me some samples, I can reverse engineer and I can build those models for you, and those would be the basis of what I can do. And then the conversation hopefully then becomes a lot more shorter, a lot more focused about what we can do as opposed to what they have internally, what the competition have. And so this is something that we've done for the US. Like I said, 56,000 assets all modeled. The real product here is basically will show every single wind turbine in the US. These are ones we don't have. And I think we have the first conversation with a customer, I think, within this quarter, showcasing this and beginning to have that different level of conversation that we couldn't do before. So this is on the modeling side. Underneath this is we have a fully automated SageMaker capability that hosts the model, hosts all of our models that we are fully trained of how to do ourselves. And I would say 3 months, 4 months ago, we didn't know what SageMaker was. The second capability here when I go to is to show the left-hand side. Is that now that we get to get data, how do we begin to have a data ingestion pipeline that can come closer to the customer, closer to the customer? So for that, I don't have anything UI fancy, UI, but I have AWS console. So I think here, to be able to, let me, the idea here or the caveat is for the demo purposes, I don't necessarily have Greengrass cores that are deployed at a customer. Even if I did, I couldn't demo it. But what we have done for the demo, which is what we need for customers that we want to go after, is that we have simulated a Greengrass core instantiation for our China customers, and then we deployed it in Singapore. For our European customers, and we've deployed it in Frankfurt region, AWS Frankfurt region, and then the US, and we've deployed it in Ohio, just not where we actually operate, which is in US East. So we have 3 implementation representing basically 3 regional customers from the 3 different continents. Then what you have is that you need an IoT core. This is basically the message broker where all your data would come in, and then you decide how to process it. And then after the IoT core, and then you have some rules, then you get to persist data. Most of the SCADA data or the time series data, where we have the example here, is persisted for us in S3. But also where we've explored how we can store that data in a different, a more of time series type of database, and IoT analytics provide that, so we can interact with it a lot more easily. Interacting with data in files in S3 is very, very costly in terms of opening the file, processing it, and closing it. So let me show some of this infrastructure and that we've built. So when you go to the services, this is on our development environment. Like I said, we've worked with Tensor IoT and AWS in one account where they showed us how this could be worked, pipelined this, automated of how you get to deploy this. We took it over and we replicated it in our environment in no time. So the first capability you want to look at is how do you basically establish a compute infrastructure for, let me move from, for your, so the ideal situation is that you have an edge. Am I showing? You're not moving. Okay. Let me see here. Okay. All right. I want to try and minimize this. I'm supposed to be showing my browser, but it's not. Can we get help? All right, I'll use that. Thank you. Perfect. So absent of deploying this Greengrass core in an edge device, we just created 3 instances in these different regions and to deploy them. And the same way you deploy them in here, you get to deploy them on a, you get a computer, you get a SCADA system, anything that's closer to the edge that has some compute and Linux compute and storage you could do. So here, I think one thing that's very critical, I was going to do a demonstration from a customer site. You look here, most of the IoT I think messaging happens through MQTT. When you talk to a traditional IT department, they don't understand what that means, and that's a different port 8883 to open, and that you have to go through a full IT process before you can open that outbound. So once you establish your infrastructure, you have to open that port. So we have that for, we have Ohio, we have Singapore, no, it's not Sydney, Singapore, same deployment script, Singapore. This is representing our China customers. Currently, we serve that from our US location. As we move into phase 2s with China customers, we are in the process of getting our AWS China, which is a different beast. And then for our European customers, same again implementation. This is basically the infrastructure in there where we're deploying the Greengrass core. So the second thing I wanted to show is, now that you have these virtual, it's called edge devices, then the AWS IoT is your registry, where you begin to register these external edges, and then you need to establish channels and pipelines of how you communicate with them. So once you build that, you go to Greengrass core here. The registry, you say, what groups do you have? And so I don't have any groups in Frankfurt, so I have to go back to where my platform is deployed, which is in US East at least. And then we have 3 groups. I have fictional names for the customers: Alpha, Delta, and November. Alpha is in Frankfurt, November is in Singapore, and Delta is in Ohio. So these are basically the groups. Groups is basically this conceptual grouping of what happens at a particular edge. What do you have there? You have cores, you have devices, you have some Lambda functions deployed on those Greengrass cores, etc. So I think that's one concept. The second concept is whatever you have in that core, in that group, where does it send information to? What is the subscription? Which is basically in the picture here. So now you have a single kind of registry, single MQTT broker where you have to send your data. And this is how you set it up. You have the IoT, and then you choose the topic. Familiar with the PubSub architecture or designs, then you publish from this particular source into this target, which is the IoT, and then what do you, cores, again, this is, you associate the core to the group, and then finally, we don't have any devices, so this could be devices. You can have a Greengrass core, and you can have edge devices that communicate locally with it, and then is the one that takes those messages into the cloud. Most importantly, I wanted to show for each, say, alpha customer, we have an alpha group. That group has one core, right? And then what does that core? A Greengrass core is basically this AWS cloud version that operates locally. What are you going to deploy in it? So I have one Lambda function that does many things. And I want to click on it and showcase what Prashant showed earlier. As a Lambda function, you get to specify, because now you're talking local, which file system do you want to give it access to. I want to mention here in terms of memory limit, when you work with Lambdas in regular serverless cloud, you have a limitation of 3 GB. So when you want to process anything that's going to require more than 3 GB of RAM, you're going to have that limitation. And we've ran into that. Some of the files we have to process have more than that. When you work with Lambda locally, we're able to configure it up to 8. And I don't know what is the limitations. I need to ask. But we've done 8, and it's been working fine. So you get out of those limitations that you had in the cloud working locally. The point I'm trying to make here is I'm literally basically looking at the code for this Lambda function here. The point I'm trying to make is this code wasn't built part of this. This code was taken as is from current pipeline that I have, because I run this process here of organizing, mapping the data before I get to process it in the cloud today. And I've been able to take that logic associated with the Lambda function that's running in Greengrass, and now it can run on a customer side. And what this would do to a customer, a big customer in Europe, for example, Acciona, I can now have conversations with them saying, I already have about 6,000 of your assets onboarded. This is how you send data to me. I think we can change that to make that processing of the data faster, more automated, and my results more accurate. And the way to do it is if we run this logic closer to the source, then from the 3 laws that you have, we have less weight coming in through the wire, we have more processing done on the edge, and I get close to ready data that I get to process. I think that's the main thing that we have here that I wanted to show in terms of. So I think what I've been able to at least highlight and emphasize is our ability to build this infrastructure for the IoT, which I have now completely pipelined, the same way I've done it in Singapore region. I can do it in a local machine, and we've done it locally in the office in a local machine. I can go to a customer site, use the same scripts, and deploy that, and none of the rest of the architecture will change on the cloud side. So, and I think being able to do that in 3 months is not something capability that my team had. It's a capability that I've learned quickly, and now that I have owned with a partnership with AWS and the recommendation of Tensor IoT. All right, so with that, I'll give it to Prashant.
Cool.
All right, and you don't need me here, I guess.
Cool, thank you, Amin. So what I would like to do is sort of just go to the third part of this session, which is about the AWS IoT partner ecosystem. And when we look at partners, there are two kinds of partners, right? There are independent software vendors who run applications on AWS or integrate with AWS services. And there are consulting partners that essentially are professional services firms that design, architect, build, manage, and migrate applications on AWS. Now, one of the things that we're doing here today is if you look at the consulting partner space, we have service delivery designations. Like these are designations given to consulting partners that essentially have demonstrated a track record of building certain capabilities. Like for example, you could have a consulting partner that's got deep capabilities in building serverless applications. Or there could be a consulting partner that has capabilities in running and migrating government workloads using the AWS GovCloud infrastructure. So for example, 47 Lining is a Hitachi Vantara company, and they're a premier consulting partner, and they built a serverless enterprise data lake architecture that brings in all of the industrial data from on-prem, built it into the cloud, and you can really start doing interesting things in the cloud. They also built a time series data connector. So what we're announcing today is a service delivery designation for IoT, and it includes AWS IoT Core, includes AWS Greengrass, and includes AWS IoT Analytics. And the reason these service delivery designations are important, because if you look at AWS IoT Core, it's quite fundamental and foundational, where it allows you to connect your devices and interact with various cloud applications, with other connected devices. It lets you build applications without having to really worry about the infrastructure that runs these applications. AWS Greengrass brings in those AWS capabilities to the edge, and now you can really develop edge applications and don't really have to worry about whether the device is connected or not, and then start doing things in very simple terms like Lambda interfaces without having to worry about the embedded programming. And then AWS IoT Analytics, it's a very managed service, fully stacked analytics capabilities for all of the IoT data. So you have to really start building out analytics infrastructure. So what these three designations are doing is that we are launching these service designations today. And these are our set of consulting partners, which are launch partners. And then you'll see Tensor IoT that work very closely with Sentient Signs in building that solution that we just showcased. Deloitte, a very large consulting firm, it's got capabilities in AWS IoT Analytics as well as AWS IoT Core. Now, I think the last key point that I'd like to leave you with is that when we look at the AWS IoT partner community, we look at this from the context of edge to outcome. And what we mean by that is if you look at the edge ecosystem, that spans silicon vendors to gateway OEMs, and then you look at the ISVs that are really trying to drive towards more IoT applications and ML applications using IoT data. So let me give you an example, right? If you take Uptake, they're essentially an industrial analytics partner of ours, and they're very focused on delivering to industrial outcomes. They worked with Palo Verde, which is a large nuclear, one of the largest nuclear reacting companies, and they essentially helped to optimize the maintenance of these reactors. They were able to reduce the maintenance by 40%, which essentially translates to like $10 million. So this is kind of an outcome that we want this partner community to be able to drive. And one of the key things to do in here is looking at how do we make the set of edge products, that whether these are silicon products or gateway OEM products, easily connectable to the various AWS services. And then with a set of ISV partners, any customer can stitch together a solution that's very repeatable and well architected for certain targeted outcomes. So we're making a big push to sort of help our partners build solutions that our customers are looking for. And one of the ways in which we're sort of enabling this with the consulting partners is the service delivery designation. So in essence, what I would like to do is sort of go back to this question that I started with, right? I mean, you just saw sentient signs that talked about if you were to know the state of every one of those wind turbines, including the material science properties, you can now really start to do very interesting things with that data. You can not only improve the maintenance and the lifetime of these assets, you can essentially lower the cost of energy. So I think what I would like you folks to think about is now that you're able to easily know the state of your assets, what kind of business problems would you solve? And what I would like to thank you all for taking the time today. And we're going to probably have time for questions, and we could be hanging out here. So feel free to ask us any question that you might have. And thank you for taking the time. And what I would also ask you to do is there are various sets of sessions, workshops, chalk talks. There's an IoT pub crawl later today. Spend more time to sort of understand a lot of these use cases and solutions that are being built on AWS and sort of understand some of the services. There are going to be a whole host of other services that will get announced over the next couple of days. So take the time. Thank you again. And Amin and I and Robin here will be here to answer any questions. Thank you.